Hello, everyone. I want to take this opportunity to thank the conference organizers for such a great conference and also for the award that I was presented last evening to my great surprise. Thank you. And right after that award, as I was stepping down, they said, oh, and by the way, you're speaking on the feed additive panel tomorrow. So I think the award was just to kind of butter me up, really, right? So yeah. Hopefully, I have some slides. So I just put together some thoughts on feed additives, some insights. I think there's some things we need to think about as an industry. We do have some significant challenges in terms of feed additives. When you look at feed additive development, it's very high cost. And if you think about it, there is fairly limited global market for feed additives. We heard yesterday that 80% of enteric methane emissions are from low and mid-income countries. So a lot of those countries are not going to be using feed additives. And then what is the market penetration? The feed additives we have right now work best in a TMR situation, yet we know that most of the enteric methane emissions are coming from our cow-calf herds, at least in North America and I think globally. So it's very challenging to get a feed additive administered to animals in extensive systems. So as we just heard from Ermias, we really need to think about delivery technologies for extensive systems to tackle where the emissions are coming from, whether that's water, in a bolus, or slow release, or as Ermias mentioned, other avenues. Okay. Some other challenges, I think, are impediments at the adoption level. One of the main things is if you're putting a feed additive into the ration, you're increasing the cost of that ration. And who pays for that? Is it, carbon markets, government subsidies, consumers? Are they going to pay more? It's a major issue for on-farm adoption. So that's something we really need to think about. What is the revenue for the producer of putting a feed additive to reduce methane? Right now, it's not very much. The other thing are, what are the long-term effects? A lot of the studies that are published on feed additives are short-term, often Latin squares, so we don't really know what the long-term effects are over an entire lactation or over an entire production cycle. So is there adaptation of the rumen over the long term? Are these additives less effective over time? The other thing that intrigues me is, are those additive or mitigation strategies, are they additive? So if you have genetically selected animals for low methane emissions and you feed them a feed additive, is A plus B now additive, or is there some overlap in that? Right? Or if you're feeding additive A and additive B, are those additive responses, or is there some kind of overlap? Or is there synergy? We don't know a lot about additivity. And then, of course, we always have to keep safety in mind when we're developing feed additives for the farmer, for the animal, and for the consumer. So right now, I would say we have two major feed additives that are shown to be effective for methane mitigation. We have 3-NOP. It's well researched. It's got several meta-analyses that have been published looking at responses over various conditions, et cetera. Approved in 68 different countries around the world, yet adoption of that product, I think, is still quite low. And then the other category is, I would say, haliforms or bromoform type products, whether it's the red seaweed asparagopsis or synthetic bromoforms. And I looked in the literature to try and find a good meta-analysis, and I couldn't find one. But Ermias, I'm really happy that you're publishing one. So I just went through the literature and did a search to say, what do we know right now in terms of dairy and non-dairy? And I found 9 studies for dairy cows, 4 studies for Asparagopsis armata, 4 studies for Asparagopsis taxiformis. Those were the whole seaweed product that was ground and pelleted in most cases, and 1 study with synthetic bromoform product. And then the non-lactating animals, it's a bit of a hodgepodge. 3 beef feedlot finishing type studies with Asparagopsis armata infused oil, 5 studies with Asparagopsis taxiformis whole product, and that was beef cattle, sheep, and goats. 1 sheep study with Asparagopsis taxiformis infused oil, and then 3 synthetic bromoform studies. So it's a hodgepodge of products, a lot of different products and different diets and different animals and what have you. So I just put that all in a spreadsheet and said, what can I get out of this? Hoping that somebody else will come along and do a real meta-analysis. But I'll just show you some, I just, plotted some data there. And on this graph here, you see on one side is the non-dairy, and what I'm showing is as you increase the bromoform concentration in the diet, you reduce methane emissions expressed relative to dry matter intake. So I call that methane yield. And it's quite clear in dairy and in beef, although the response in beef is quite a bit. Oh, sorry. What have I got here? Non-dairy. Yeah, sorry, on that side is non-dairy, and as you can see, in both cases, you're clearly reducing methane emissions, but you can see in the beef studies, you get quite higher efficacy. So in some of those studies, you have almost 100% reduction, and I put those circles around the dots to show the synthetic bromoform treatment. So every dot on those graphs is the treatment mean compared to the control. So efficacy across all those different products and different animals and what have you, it's quite clear that those products are reducing methane emissions. And if we drill down and look at the different products and the different diets and what have you, we can probably explain some of the variability in the data. But what producers want to know is if they reduce methane emissions using those products, what happens to animal performance? And I plotted some of those data. And these are the data for dairy cows. So on one side, you have dry matter intake, and the other side, you have energy-corrected milk. And what on the x-axis, you have the % reduction in methane yield. And what I got out of this was as you reduce the methane yield using those products, you get over a certain level, and it's pretty low, 10 or 15% reduction in methane emissions, you start to see a reduction in energy-corrected milk. And on the other side, you start to see a reduction in dry matter intake. That is a concern. Now, okay, the energy-corrected milk, a lot of the studies are short-term, crossover type design. So, but it's telling me that we need to do something to understand what's happening in terms of the dry matter intake. And when I plotted the data for beef, exactly the same. You get over a certain level of reduction, and it's quite low, you start seeing reductions in dry matter intake. In some of the studies, it's not significant because of the very low number of animals per treatment. But what about performance in beef cattle? Here, it's quite difficult to make a comment on that because there's relatively few studies that are long-term that really looked at average daily gain and feed conversion efficiency. But what I saw from that, there are certain studies that show an improvement in average daily gain, improvement in feed conversion efficiency, and at the same time, studies that show no improvement. So I think we have a lot of work to do before we can successfully feed bromoform-based products. So in conclusion, when examined over all those different products, clearly methane can be reduced using bromoform, but we have some challenges in terms of reducing dry matter intake when we're reducing methane emissions with those products. And that translates into reduced milk production and reduced animal performance. So with that, I await your meta-analysis, Armias.
Thank you very much.